Video Lecture 16E, Buffers. Buffers are solutions that are able to resist drastic changes in pH, even when small amounts of a strong acid or strong base are added. In order for a solution to be a buffer solution, it must contain a significant amount of a weak acid and its conjugate base. These amounts must be in a ratio in which so that the pH does not change by more than one pH unit. Buffer solutions are used in chemistry to keep reaction mixtures at a certain pH. There are also biological applications to buffer systems. Your blood, for example, has a buffer system that keeps the pH right around neutral. This buffer system is made from the weak acid carbonic acid and its conjugate base bicarbonate. Both of these species work to maintain the pH of your bloodstream around 7.4. Even small changes in pH can lead to severe illness or even death. The way that this system works is that when a strong acid containing a high concentration of H3O plus is added to your bloodstream, it'll react with the conjugate base component of the buffer. This is the bicarbonate ion. This reaction will consume, as long as it's a small amount, this reaction will consume all of the strong acid to form more carbonic acid, and the pH of your bloodstream will not drastically change. Also, if a strong base containing hydroxide ion is added, it'll react with the weak acid component of the buffer, the carbonic acid. This reaction, as long as the hydroxide ion concentration is relatively small, will consume all of the excess hydroxide, forming more bicarbonate ion, leading to an overall maintenance of the pH of your bloodstream. To make a buffer at a certain pH, there are two factors that we need to take into consideration. First, the pKa of the weak acid mainly determines the pH of your buffer. For example, the blood buffer, carbonic acid, and bicarbonate keeps the pH around 7.4 because the pKa of carbonic acid is close to 7. To fine-tune the pH of your buffer, you will need to choose a ratio of the conjugate base to the weak acid concentration that is between 0.1 and 10. A useful equation to use to perform calculations for preparing buffers is the Henderson-Hasselbalch equation, which is a rearrangement of the Ka expression for a weak acid. We will not go through that derivation here, but if you'd like to try on your own, you would need to start by taking the negative log of both sides of the equation. Then you can use some properties of logarithms to rearrange the equation to get the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation says that the pH of a buffer depends on the pKa of the buffer and a logarithm of the ratio between the conjugate base concentration and the weak acid concentration. The Henderson-Hasselbalch equation works very well because when a weak acid is in the same solution with a good concentration of its conjugate base, the acid ionizes less. This is known as the common ion effect and is an application of Le Chatelier's principle. We will see more of this when we talk about solubility. The Henderson-Hasselbalch equation can be used in any case where you are dealing with a buffered solution. We are going to do a sample calculation involving a buffer solution. We will consider preparing a buffer by mixing 25 milliliters of 0.2 molar acetic acid and 75 milliliters of 0.2 molar sodium acetate, a weak acid and a salt containing its conjugate base. We will first calculate the pH of the buffer solution that results from mixing these two solutions together, and we will look at what happens to the pH if 10 milliliters of 0.1 molar HCl is added to this buffer. Let's first calculate the pH of the buffer that we are making. To simplify things for us, we will work in moles. The main reason for this is when you mix two solutions together, you dilute each solution, resulting in a lower concentration for both species. This would require you to do two separate dilution problems and worry about the total solution volume. To make things easier, we can work in moles, which is fine because the Henderson-Hasselbalch equation deals with a ratio between the concentrations of acetate and acetic acid. In this ratio, the volumes of the solutions will cancel out because they will all end up in the same buffer solution. So we start out our calculation by calculating the moles of acetic acid and acetate in our new buffer solution. The moles of acetic acid can be found by first converting the volume of the solution, 25 milliliters, to liters, and then multiplying it by the molarity. This gives us 0.005 moles of acetic acid. We can do a similar calculation with the acetate ion, where we have 75 milliliters of 0.2 molar sodium acetate. Notice that the sodium ion is not included here because it's a spectator ion. You can also consider that it is a neutral ion. It would not participate in the buffer action of this solution. We end up with 0.0015 moles of acetate. We can now substitute into the Henderson-Hasselbalch equation. Note that we change the ratio from concentrations into the moles of acetate, which is our conjugate base, and the moles of acetic acid, our weak acid. We can plug in the Ka of acetic acid along with the moles that we found previously. And we get a pH very close to 5.22. This is the pH of the buffer solution before any strong acid or base is added. And we can use this for comparison. Now we will calculate the pH when we add 10 milliliters of hydrochloric acid to the buffer, a relatively small amount. So first, let's consider that HCl is a strong acid. This means it will completely dissociate when dissolved in water and form exclusively H3O+ and chloride ion. We will not consider the chloride ion since it is a neutral cation and does not affect the pH of our solution. This H3O+ will then react with the basic component of our buffer, the acetate ion, to form more acetic acid. So we expect that the pH will change by a small amount, but this small amount will be less than the original pH of the buffer, since we are forming more acid. One important thing to note is that when we're reacting a strong acid or base with a weak acid or base, or even another strong acid or base, the K will be very large for this reaction, meaning that this will be a very spontaneous reaction. Reactions with very large Ks have easy to figure out X values, or extent of reaction values. It is dictated by the limiting reagent of the reaction. So we'll use an ICE table to help us figure out the new concentrations of our acetate ion and our acetic acid ion. We already know how many moles of of acetate and acetic acid we have, but we now need to figure out the moles of H3O plus we'll have. We can figure this out by multiplying the volume of the solution by the concentration of our HCl to give us 0.0010 moles of H3O plus. We next need to write an equation for the reaction between H3O plus and acetate, which is the reaction below. Note that this is a proton transfer reaction. The strong acid will donate a proton to the acetate ion to form acetic acid. Water is another product of the reaction that won't affect the pH of the solution. We can begin our ICE table by putting in our initial moles. We initially, before the reaction commences, have 0.015 moles of acetate ion and 0.005 moles of sodium acetate. We also are adding 0.0010 moles of H3O plus. Notice between the two reactants, the moles of H3O plus is less than the moles of acetate. This means that our H3O plus will be our limiting reactant and will be completely consumed in this reaction. We will use this number of moles as our change values for all species in the reaction. Again, we can do this because this reaction involves a strong acid as a reactant, meaning the K is very large. So we know that all of the H3O plus will be consumed, and 0.01 moles of acetate will be consumed, while 0.001 moles of acetic acid will be made. So at equilibrium, or the end of the reaction, we'll be left with 0.014 moles of sodium acetate and 0.0060 moles of acetic acid. We now know the amounts of acetic acid and acetate that are formed after the reaction takes place. Our last step is to substitute these values back into the Henderson-Hasselbalch equation. The only thing that changes here is our ratio, since the amounts of acetate and acetic acid have changed. The final pH turns out to be 5.11. Note that the pH decreased a very small amount, about 1/10 of a pH point. This is considered a very small change. In comparison, if you add HCl to pure water, the pH will drastically decrease from neutral to a very acidic solution. The same type of calculation can be done if strong base is added to your buffer.